Okay, when we left off last time, I had done the first page of Lewis structure worksheets with you and shown you how to draw the dipole arrows and do the formal charges. And then I got you a little bit further with the ammonium ion and sodium sulfide, and I asked you guys to go in, draw all of them, do the dipoles on every structure and the formal charge. And so this is so you guys can check what you did. I'm not going to show you anything new in this video. This is just checking your answers. So, ammonium ion would have this Lewis structure. And typically, when you have something with a charge, a lot of times you'll see it like so with a positive charge around it. It's not wrong if you forget to do that. Because this one is an ion, guys, and you know it's an ion because see it has a charge. For an ion, I would not ask you to draw dipole arrows. And I'm not going to ask you on the test to draw the arrows if there aren't supposed to be any. So you wouldn't have to draw them here. Okay, in calculating the formal charge on the ammonium ion, we would get that each hydrogen has a 0 formal charge and that the nitrogen has a +1 formal charge. And if you'll recall, I said that last time that helps us check out this because all of them, 0, 0, 0, 0, and +1 add up to be the overall charge on the ion. Okay, the next one we need to check is SO3. Okay, so I tallied them up. I got 24 electrons to use. Okay, that's my structure. Dipole arrows. Every one of them is going to point towards the oxygen. And on this one, doesn't matter where you put the double bond, okay? It could be at the top oxygen, the right oxygen. You guys might have drawn this more like a T shape, and that's fine. Actually, that double bond is moving around on those oxygens. That's where the resonance comes in. It's not always on, like if we call this oxygen 1 and this oxygen 2 and this oxygen 3, that double bond's moving around. Sometimes it's on oxygen 1, sometimes 2, sometimes 3. So that's a little bit of that resonance. That'll come into play later when we're doing polar, nonpolar. When we do formal charges on this, sulfur has a +2 formal charge. The double bonded oxygen is going to have a 0 formal charge. And then those single bonded oxygens are going to have -1 formal charges. Okay? So, like how I got this one is I said 6 minus 2, 4, 5, 6. 6 minus 6 is 0. How I did this one is I said 6 minus 2, 4, 6, 7. 6 minus 7 is -1. That's the same math that I used for this one. The sulfur, I would have said 6 minus 1, 2, 3, 4. And that's how I got +2. Okay? At this point, I want to take y'all back to something we did when we started this. We were doing Lewis dot symbols. Remember, like the Lewis dot symbol for O, because it has 6 valence electrons, we would have done sulfur because I did the third period elements. But for O, its Lewis dot symbol would look like this, right? And if you'll recall, I told y'all when you draw the Lewis dot symbol, everywhere there's a single electron, that's where O would like to form a bond. So see, elements in group 16, they're all going to have this kind of Lewis symbol. So elements in group 16, see, they like to form 2 bonds. They don't have to. They just like to. But look at this structure right above it. When the O formed two bonds, its formal charge was 0. But see, when it doesn't do that, when it does something besides what it wants to do, it will not have a 0 formal charge. Okay? And look, you don't have to remember that, but it's very useful if you do remember that in checking your formal charges. Okay, so that's SO3. Moving over to chlorite. That one had 20 electrons. And we actually, for those of you who joined the conference this morning, we talked about this one in that online conference. Again, the angles of your bonds can be something different from that. You could have drawn it just straight, or you could have drawn it like at right angles. That doesn't matter. Those angles you drew. We could, on this one, put brackets around it and show that it has a -1 charge. But when we're doing formal charges, we should get that both O's have a -1 and the chlorine has a +1. And we see that all that adds up to be a -1 and a +1 and a -1 adds up to be -1. So we're checking that. That's a good, showing us we're doing it right. On this one, you would not draw dipole arrows, because if you look at the periodic table, and if we just take that small section where we have oxygen, fluorine, sulfur, and chlorine, this is part of the periodic table, the trend for electronegativity is increases bottom to top and increases left to right. And so what that means is, because of where the O and the Cl are placed, you can't tell which one's more electronegative, okay? So I wouldn't ask you to do a dipole arrow on this one. What you'd actually have to do, if this didn't have a charge, is you'd have to look it up on a table of electronegativities and actually compare numbers. But again, because it has a charge, you wouldn't do a dipole arrow on it. Moving along to the next one is the sulfite ion. Okay, we had to show 26 electrons on that one. Okay, and so when we get that one drawn, oops, it doesn't have a carbon, does it? You have something. I should have used my bigger. Okay, this is what we have for its Lewis structure. When we do the formal charges, we'll get a -1 for each O, and we would get a +1 for the sulfur. I wouldn't ask you for dipole arrows because this has a charge, okay? So I wouldn't expect you to draw them. If you had drawn them, you would have put them towards the oxygen, okay? But again, on the test, if it has a charge, I'm not going to ask for them because it's an ion. The next one you had to draw is CH2O, which is formaldehyde. Now, this one's a little different because we have 3 different elements to put in it, so we're getting a little bit more challenging on our Lewis structures. The central atom is going to be the C. And so y'all know if there's only one of them, like if you look at this other one over here, S is the central atom. That's easy because there's 1 S and 3 O's. But what do we do in here when we have 3 different elements? A lot of times the central atom is what's written first, okay? But y'all, if you have a carbon, carbon's always the central atom. For those of you who get to go on and take organic chemistry, carbon's always your central atom. So what you'd have to do is you're going to put carbon in the middle, and then you're going to attach the 2 H's to it and the O to it, and to make it satisfy the rules, you're going to end up having to double bond that O. Remember, you never double bond a hydrogen, okay? The next thing we would do is go in and do the formal charges. They're all 0. The C's, both H's, and the O, all 0 formal charge. Okay, dipole arrows on this one. The carbon to oxygen dipole arrow points towards the oxygen. You do not draw dipole arrows on carbon-hydrogen bonds. Okay? You never do that. Had y'all drawn them, you might have pointed them towards the carbon, but we don't draw dipole arrows on carbon-hydrogen bonds. How do we know that? We just learned it. Like I just said it. That's how you know that. Okay? Organic compounds have millions of carbon-hydrogen bonds. You never put a dipole arrow on them because carbon-hydrogen bonds, there's no difference in electronegativity between carbon and hydrogen. So that's just one of those we just remember because lots of compounds have carbon-hydrogen bonds. Okay. The next one we need to check is carbon dioxide. And you guys should have come up with this Lewis structure for carbon dioxide. When you did formal charges for everything there, you should have got a 0 for everything. And the dipole arrows would point straight out from the carbon to the oxygen. Okay, next is thiocyanate, SCN. We've got 16 electrons to use, and there's actually more than one way you could have drawn this one. And I'm drawing them both ways. Both of these are going to check out as far as if you look at both of them. Every atom has an octet in both structures. Also, both structures have used 16 electrons. So either structure would be acceptable. Now, there is going to be a difference on the formal charges depending on which one you did. Like the top one, it would be 0, 0, -1. And the bottom one, it would be -1, 0, and 0. Okay, so the numbers, formal charges are different, but in either structure, they total up to be -1. This one is an ion, so we would not draw dipole arrows on it. Okay. Then checking on the back page, nitrate, 24 electrons. And the Lewis structure, 24. Okay, there you go. Again, doesn't matter which O you put the double bond on because that double bond's moving around in between O number 1 and O number 2 and O number 3. You would not have put dipole arrows on this one. I wouldn't have asked for them because it has a negative charge. But before you watch this video, this one, you guys wouldn't have known that. So you guys probably would have drawn them like that. And it's okay. I mean, you're practicing drawing them. So if you drew them like that, you did the right direction. But I wouldn't ask for them because this is an ion. The formal charge on these single bond O's is -1. The double bonded O is 0. And the nitrogen in the middle has a +1 formal charge. And again, that checks out. The sum of all the formal charges equals the sum on the ion. Okay, the next one. So look, NO2. Step 1 of drawing a Lewis structure is to add up all the electrons, right? That's what I've been doing up here at the tops of them. I come up with 17. Is there anything odd about that number? Pun intended. It's an odd number. So if you tally up the electrons and you get an odd number, the first thing you need to do is check that. Did I do that right? And when you check it, you still come up with 17 electrons. So you know before you ever draw this one, it's going to be an exception to the octet rule because there's no way you can be working with an odd number of electrons and then make everything have 8. This structure is going to end up somewhere having a lone dot on it. Okay? And when I draw it, I end up here. This structure will get everything closest to an octet, as close as it can get to 8, but nobody has more than an octet. Okay? And so we knew, again, because this was an odd number, we knew we were going to end up with a little electron by itself somewhere. And if you're following the steps that say place left over on the central atom, that's how it ends up on the nitrogen. Okay? The dipole arrows on this one would have pointed towards the oxygen in each case. And the formal charge, that single bonded oxygen is -1, that double bonded oxygen has a 0, and the nitrogen has a +1 formal charge. And now always in class when I get to this one, I like to talk about this. Have you guys ever heard of a free radical? Okay, so not like radical in terms of your political beliefs or something, but in terms of science, a free radical. This is a free radical, NO2. It's a free radical because it has that one little electron, that lone electron. What did we just say earlier about when we were drawing those Lewis dot symbols, I showed you like for oxygen. And we said that where there's lone electrons, it wants to form bonds. That's the same thing here. This free radical wants to bond with something. Guys, they're very reactive. Remember when we did the lab where y'all took the piece of copper wire and you put the nitric acid on it and it gave off the brown gas? Nitrogen dioxide was the brown gas. And we put them under the hoods. Y'all didn't need to be breathing that. It's harmful. If you think in terms of just life and health, you might have heard of free radical. You've heard of antioxidants, I know. Okay, maybe you haven't heard of free radical, but you've heard the term antioxidant. And think about that for a second. Where have you heard that? In our diet, it's good to have food that's high in antioxidants. Like what kind of things? Y'all have probably heard, hey, dark chocolate is better for you than milk chocolate. That's because dark chocolate is higher in antioxidants. I mean, chocolate's probably not good for you anyway, but if you really need to claim that it is, it's dark chocolate that's good. You've heard red wine is better than white wine because red wine is higher in antioxidants. Maybe you know things like pomegranates, high in antioxidants, green teas, etc. And free radicals have been linked to causing cancer. That's what a lot of people, I've known people that were diagnosed with cancer, and they'll do the treatments, the medical treatments of radiation or chemotherapy. But another thing a lot of cancer patients do is they change their diet. They start to eat foods that are higher in antioxidants, maybe things they didn't eat before. Free radicals have been linked to causing skin damage, and that's more apt females are more apt to do creams on their faces than males, but we're all susceptible to skin damage from the sun. And so we put creams on them that are high in antioxidants that help combat aging and stuff. But that's just a little bit about antioxidants and what they are biologically. Antioxidants environmentally, that's ozone depletion. It's linked, it's not antioxidants, but it's linked to free radicals. Okay, when ozone breaks down, it produces a free radical, which breaks down more ozone. So there's a lot of connection there. Hopefully y'all found that interesting. I always find the practical stuff interesting. Helps me remember the harder stuff. Next one, hydrogen peroxide. I'm going to zigzag mine when I draw it. You did not have to zigzag it. Okay. Formal charges are all 0. Dipoles are going to point towards the O. We're not going to draw a dipole on this bond because it's an O and an O. They're sharing them equally. Okay, and then the last one, C2H2 is going to end up looking like this. We're going to get all 0 for the formal charge. And the dipole, remember, we don't draw dipoles on carbon-hydrogen bonds, and we wouldn't draw a dipole here because it's the same 2 atoms. So there are no bond dipoles to draw on that one. Okay, and that should check your worksheet, and we'll pick up here on the next lecture, and we'll work on geometry and that kind of stuff.